Okay, so we are going to start in NanoCAD. I'm going to make a new drawing. And I'm going to insert reference image of our part. Image from file. We're going to model something small and easy today, because I hope to do it all in one go from start to finish. This is one side. It was D, so now we need 7, 8, 7, 9. Here we go. I'm going to save it. Drawing 15. Okay. When I sketch on reference pictures, I like to change my line color to red. It's much better to see. Unless the part is red, of course, then you want something like bright green. I make my reference pictures by scanning the parts flat. You could scan them in 3D, which is much more advanced and useful for bigger, more complicated parts. But for small parts like this, the flat 2D scan is perfectly fine. But I also have the part itself in my hands, so I can rotate it, I can look how certain features look from the side, and I also have calipers that I'm going to be using to take some dimensions that are hard to take from the reference itself, or the dimensions that cannot be taken, like the third dimension, the width, because we have height and width, length, but we don't have height, so we'll have to check the height with the calipers on the real part. Okay, so first thing we have to do is to align the parts. As you can see, the parts were just laid freely on the scanner, and we could theoretically draw them like this, but it's much more easy and convenient if we have parallel lines. Everything is either horizontal or vertical. So first thing we have to do is rotate the part, both those images, so they line up with our grid. First, what I'm going to do is find the center of this circle. I'm going to do this with circle with 3 points. I'm going to choose 3 points, and it's going to specify a circle. The more accurate you are with your drawing, the better the final part will be. So you have to kind of aim. There we go. We have now the center of the circle. Now I'm going to every part needs a different approach, so I'm going to be thinking as I go along how to do this. Basically what we would need now is as long as we can vertical or horizontal part on the line, on the part itself. Because the part itself is very curved and doesn't have straight lines, we will have to use only those connectors. It's not ideal that they are very short, because the longer the line would be, the more accurate our line would be. Okay, so back to the topic. Now we need to pick up the same angle that the connectors have. So again, we can use either of these lines. Again, we could even use this line, but it's a lot shorter than this line, so we're going to choose one of these 4 parts. We could use this one, but because both parts are basically the same color, it will be harder to find a correct angle. So here is actually a much better place to do this, because the part with the background has much bigger contrast. So again, we're going to zoom in, not too much, because if we zoom too much you can't see anything. And we're going to zoom just the right amount, pick the point on the line, and now we are not going to pick the other point because it's harder to again aim. We're going to go past the line and align those 2 parts so they're same angle, and there we go. So now this line will be our reference. Now we need to rotate. This picture so this line is parallel to our grid lines. The way I like to do this, we're going to move it a little so we have space. I like to rotate the reference so the line is in the right upper quadrant. The angle here is not really important. Now we make horizontal line, we mirror our first line, and now if we rotate from this point, we can just grab this point, and now our first line is horizontal. We can rotate it by 90 degrees, so it's more convenient. Oh, come on, F8, there you go, and now our line is at a perfect angle. We are not going to be drawing the connectors because I much rather like to model them on the part when the part is almost finished, so I won't be needing that line anymore. And now when the part is at the correct angle, the very important thing to do is to scale it. You could trust your scanner and believe that it's scanning in 1:1 ratio, especially when you told it to, when you chose it in the settings. But I find that it's not very correct, it's not very accurate, and sometimes you could have some dimensions difference, especially with big parts. So the best way is to actually do it ourselves. There are 2 ways to do this. Easier one and more accurate one. Easier one is to use the knowledge that the Lego connection points, whether they are Technic pinholes or they are big connectors, on the grid. And the grid is 8 millimeters. The features on the grid are 8 millimeters apart. So if we would have a part with 2 pinholes, at not necessarily one next to another, but you could have one here and one some place here, you know that the distance between them is a multiplication of 8 millimeters. So you could find center of those holes the same way we did for this one, measure them, count how many 8 millimeters should be between them, and scale the reference appropriately. I find that it's not very accurate. Sometimes you could introduce error into this part, especially if the pinholes are very close to another. So actually the better way is to find the longest distance on the part that you can, draw it, see how long it is, and then measure the actual part with your calipers and use this measurement to scale the part. It's much more accurate and I like to do this way. Alright, so I'm looking at my part. Sorry, I don't have the camera on the part. You can see what I'm doing with my hands, but the stream was very last minute, and it's because basically I can do this only on weekends, and next weekend is Christmas. Wait, no, is it? Yeah, next week is Christmas already. Next week, weekend after that is New Year's Eve. So the next time we could possibly do this would be 3 weeks from now. So that was the last time we could do this, and I'm not very well prepared, but I think we can manage it, and you'll have to forgive me because it's a first stream. I promise it will get better if I will do this on a regular basis. Okay, so the largest distance on this part is from the top of the connector to the top of the blade. I wasn't sure if the blade is in the right place, so I can touch off calipers from here and here, but I checked on my physical part and it's okay. So now I have to see how this measurement looks on the reference. Here we go. There's one line. When you draw lines that are that are tangent to arcs, sometimes it's easier to draw the line first and then move it to touch off the part. So you don't have just one shot. You can adjust the line perfectly. And there we go. Let's measure this distance. 47.28 and change. So now I'm going to zero my caliper. Okay, and I'm going to measure this length. Again, trying to be as accurate as I can, not to squish the part, because you can see that there's kind of a hinge here. So if I grab this part too hard, I can actually change the physical dimension. So I'm being very gentle here, and we have 47.04. So you can actually see that we are very close, especially the longer the dimension is, the bigger the difference can be. So if we would have from one pinhole to one pinhole and would expect the dimension of 8 millimeters, and we would get like 7.5, that would be a big error. But because we have 37 millimeters, that's a very long distance, and we have the difference of 0.23 millimeters, that's actually not that big of a difference, and I found by doing this many times to many different reference scans that my scanner scans the parts almost perfectly, almost to the almost one-to-one scale. But if I double check and correct it a little bit, the parts will be only better for that. So now I'm going to use my two dimensions, the physical one and this one, to scale this reference image to the perfect one-to-one scale. So I'm going to use calculator. I'm going to put the dimension that I want first. So it's 47.04 and divided by the dimension I have, 47.2882. And this is our scale factor that we need to scale it to. I'm not going to write this, I'm going to copy this. I'm going to scale this whole group, scale, okay. Specify scale factor, we need to change to a comma, and there we go. You can see that now the length is the perfect 47.04 that we measured from the part. So now we can expect this whole part to be perfectly scaled. Now we need to do the whole thing again to the other reference. Sometimes if the pipe is symmetrical, you can get away with doing only one side, because you know that everything on the other side is in the perfectly same place. But in this part, although it looks symmetrical, there is a small difference of this injection port. Here it's concave, convex. It's inside of the part, and here there's a dome, it's sticking out. So to basically pick up this diameter, which would be extremely hard to measure with calipers, we will have to use the other side too. So now I'm going to skip the commentary and do quickly the same thing I did with this part. What did I just do? The brain fed. Oh, I think I rotated it instead of scaling again. Scale factor. Okay, so now both of our references are scaled perfectly. We will just have to align them. We don't need this anymore. We don't even need this. We're going to align them with the pinholes. So this is what, 22. Let's make it 20. Wait, times 2. That's 34. Let's do the. Let's do 35. Okay, move this. Okay, we will just have to add a mirror line between them, right in the center. This, and we don't need anything on this reference because we'll be first working on this side, then flip it and only adjust the differences. Okay, so now we will use our center of a circle, but we won't be using our circle because it's some weird dimension that we don't know and is probably not accurate, we're going to use our dimensions of Lego pinhole that we know, and those are 3 circles. I'm going by diameters, so it's 495. It's dimension 6, diameter, not dimension, 6.3, and the last one is D for diameter, 7.4. We don't need our line, and you can see that the part is scaled very well. We can trust our dimensions of this reference, and we can now start drawing the shape of the part. You could actually, we will be using NanoCAD to draw the flat reference, and then we are going to import it to Fusion 360, and we're going to add our third dimension there. We're going to 3D model our part, and you could actually skip the NanoCAD and do this whole thing in Fusion. You could import the reference pictures to Fusion, you could draw the reference in Fusion, and do everything in one program. The reason I do this way, there are actually 2 reasons. One reason is because that's how I was trained in school. I was trained to use both of those programs, actually AutoCAD to draw 2-dimensional drawings, and Inventor back then, when I still had the license to 3D model the parts. And the other very important reason is when you draw something in programs like Fusion or Inventor, the features you draw are not constrained. So if you, for example, draw a line, you have one point that you can freely move, and you have the other point that you can freely move. So you can just draw a line. You have to draw the line, specify 2 dimensions by x and by y for this point, specify 2 dimensions x, y for this point, and then you only have line that's not moving. You could actually simplify it a little bit. You could, for example, start from one point and do horizontal and do just the length. So you could get with 3 restraints for one line rather than 4. But basically the fact is that everything you draw needs to be locked in place. So sometimes it's much better if you have complex shapes that you want to achieve, like many tangential arcs or circles. But if you are just drawing, redrawing from reference, the programs like AutoCAD or NanoCAD 5 are much more convenient to use, at least for me. So this is both faster, more accurate, and more convenient than doing this all in Fusion. Okay, so now we can start drawing. I'm going to arbitrarily start from this point. Again. There you go. We don't need this line anymore. Let me look at the part. Is this all one? Oh, it's very easy to miss that those 2 arcs, this one and this one, while they seem to be perfectly concentrical, they have different diameters. So there's this tooth right here. So that's why you also need the part in your hand to actually look at it from different angles and see some things that you may have missed just by looking the reference for. So we will have to do it like this. We'll have to almost the same length. This one is a little bit longer. It goes to this point here. Okay, we need 3 points to pick up the arc, and the farther they are spread apart, the more accurate the arc will be. So we'll start here. Here's one. Here's the second one. And now again we could use the point, but you can see that the difference right in this region can get pretty big pretty fast. So rather than specifying a point, I'm going to go past the end of the arc and looking at this region and this region, find a best way to click so the arc is as tangent as we can to the entire length. Okay, here we go. Those lines will cross here, so we can extend it. Now we will use the center of this arc to pick up this smaller arc, because those two arcs, while having a different radius, are concentrical. So we'll start from this point. Maybe not. Maybe they are not. They seem to be. I'm looking at the part. I'm wondering if they are actually not concentrical and the problem we are seeing here is real, or the reference, the scan, could be distorted, especially the different part heights here and here. Here it's very thin, here it's very wide, so we could have some distortion here, but it doesn't seem to be. They just seem to be different arcs, but that's okay. We'll just draw this arc separately. There we go. How does it look? Okay, it's just a point. We can actually pick up the center of the arc and just divide them like so. Now we can trim away all the excess. We don't need this, we don't need this. There's our nice point. We'll come back, or maybe, no, maybe let's do them now. How to do this? Okay. AutoCAD, which I was using before, had this nice feature that you could use offset. You could pick the line, and maybe I can't here. See? No, you can't. In AutoCAD you could use a line to offset and not put in the dimension and just visually lock it in place. In NanoCAD you have to know the dimension first. Unfortunately, it's very not convenient. So we're going to measure the distance between this line and this line. It's kind of a hacky way, but you have to work with the program on its own terms. 0.94, so it's probably 9.5 originally, and we're going to use this. So we put in the offset 0.95, enter. You can offset this line. You can see that it lines up perfectly. Now we need the size of those cutouts. Oh no, right, let's start here. Let's do this side, right about here. Let's do this side. Now we because we could draw the fourth line, but the angle between those two lines and those two lines would be different. We would it would be very hard to pick up the same angle, so we are going to actually make it easier on ourselves. We're going to use the left cutout we already drew. There we go, there's our center line, mirror line basically. We're going to mirror this line. Now we can be certain, I can actually prove it to you. Here we have, oh, it's not very accurate, I would have to change the accuracy, but we have around 9 degrees, and here is the same. So we now don't need this line at all. We can trim away all the excess. Now we'll just have to round off these edges. Another feature that was very useful in AutoCAD for this and isn't working, or I don't know how to do this in this program, is you could draw a circle that was tangent to 3 lines. So what I would do here normally with this corner, I would just draw a third line that's also tangent to this round of corner, and then I would just use those 3 lines to make a perfect round of corner that matches the reference. You can't do this in this program. The only way is you can use 2 tangential lines, and for the third dimension you have to specify radius. So it's not very convenient, it's not very accurate, but the other way to do this is use a 3-point circle, measure, let's do this here, measure with 3 points the radius of this corner. Oh, come on. There we go. We're doing this just to know the radius. 0.45. So we don't need this. And now we can round off 0.45. I mean, it works, but it's not as convenient, not as quick, and not as accurate. Okay, so with those cutouts done, we can move along with the part. We need this curve right here. Just by looking at it, I can see it's not one consistent curve. It could be arc that's part of an ellipse, but drawing ellipses here is it's possible, but it's not very convenient. I don't even know where they are. Draw, spline, ellipse. There we go. It's not very convenient here. It can cause problems in 3D modeling, so I tend not to use ellipses at all. I use a few arcs to approximate the same curvature. So we know that one arc starts here. There are definitely at least 2 arcs, maybe more. It will turn out as we draw, but they join somewhere here. We don't know where exactly. but we know that our first arc is still going here. And now we can see that if we made our line tangent, at some point it just drops off because here the curvature changes. We can now do the same thing from the other side. And again it drops off, and we can approximate this curvature with two arcs. Sometimes the shape is more complex, the arc might change more drastically, or there are some other geometries involved, but here we are fine with just one, with just two arcs. But now the challenge is to make them tangential. Again, in AutoCAD it was very easy to do. I won't bore you with the details, but here we have to again do a little bit of a hack job, unfortunately. Let's find the center. Here we go. .1. Now let's do TTI. So tangent, and our radius was 8.1, and you can see now that those two, the arc and the circle, are perfectly tangential. So again, trim of the excess, and we made this beautiful curve with two arcs that are perfectly tangential. We need to round off these corners. Again, we will measure them with 3-point circle. .7. There we go. We have another tooth here, this little step, but those two lines, the bigger one, the one right here, and the little one right here, are parallel. So we can actually find out the angle first from the bigger one. Okay. We can now use this as a reference. There we go. There are some more details here that I would need to create this corner, but I'm going to move along. We're going to circle around and come back to here. There's no particular reason for it. I just sometimes like to leave a little more challenging stuff for the later time. I just like to kind of go with the flow as I do this. 1.55. I'm going to shorten this line so we don't mistake it. Data for this line. This is something different. So let's just sit here for now. Okay, now we can make this corner around here. Wait, actually, give me one more minute. Oh, there we go. I put on some music, but I have to use my headphones, so you can hear it, and Instagram won't zack me for the copyrighted music. Okay. Now we can continue. Those lines. Oh no, I can't hear myself think with the music. I wouldn't be able to comment. So no music for me, but turn on the music you like to accompany the stream. We would have music if Instagram would be a little more tolerant. Okay, trim up the excess. You can see, maybe you can, I also know, I can also confirm this on the physical part, but you can also kind of see it here, that this corner, this place isn't flat. So there is a cylinder here that is a base for a disconnection point, and there is a half of a cylinder here for a disconnection point. But it doesn't really matter, we can just draw the outside dimension. We don't need to draw the line that those two cylinders merge. It would be of no use to us in the 3D modeling software, and it will come out naturally as we model this. The only thing is to remember to actually, when you 3D model, make cylinders here and not just flat, and everything will just turn out the same way as it is here. So we can ignore it for now. I don't want to catch the beginning of this arc, so we'll go back a little. Let's say here. Are those two circles concentrical? Yes, they are. So we can use this. Oh no, we will have problem with this being tangent to this line. Ah, damn it. Damn you, NanoCAD. Why don't you have so many cool options that AutoCAD has? How to do this? I think I'll have to go the other way with it. I'll have to start with the circle and now do this line again. Oh wait, since we have the angle, we can construct our tangencity. What's the action that comes from the word tangent? Let's copy that. Move this here. And because those two lines are parallel, the point where this line that's parallel to our line, basically radius, intersects with the circle, this is the point from which this line will come out. So we can move this here, we can join this back. There you go. It's perfectly tangential. Tangential. Those two circles are concentrical. You can see they have one single center. So we can move along. Let's skip the piston for now. Let's go right around here. So we have arc here. You can see that this arc with this line is not tangential. Let's check it on the physical part. No, it's very clearly not. But actually, I think that this maybe no. I thought maybe this arc would be tangential to this circle, but it doesn't seem to be. So we can just free draw this arc without worrying about any other features. There we go. When we pick up the center of this hinge for the piston, we can draw the outline. So let's just skip this for now. Skipping features in certain places can be very dangerous and can come back to bite you in the ass, because it might be difficult to remember all the places you skipped. That's why I wanted to skip those parts first. I stopped myself and I thought, let's do them now, because I wasn't certain if I would remember to come back to them. So when you have big part, try to avoid, try not to skip certain places. I mean, it will come up eventually when you import the sketch to 3D modeling software and you have some gaps here. You don't have closed profiles, you can't extrude from them, and it will be clear where you skipped something and where you need to come back and redo it. But you would have to open the sketching software again, redo this, import the sketch again to the program. It's just pain in the ass. So if you skip it, be sure that you remember to come back to it. There we go. The circle seems to have center on the crossing between those two lines, and I don't have this line yet, so I can draw it. Also, I can make up this corner because we would need another line here. So I was trying to. Oh, I'm making so many skips. Okay, let's not skip anymore. we'll just have to do some things twice to keep the entire thing a little more consistent. Let's do this offset here. Let's measure it first. Maybe here the shadow gives us a good contrast. We can pick up the end of this feature better. And the distance we are looking for is, wait, no, this what the hell? Maybe let's cheat a little. Take this, okay. Now it will be easier. 1.35 is the dimension. We use the offset command. 1.35, and now we can go crazy with the offsetting. This offsets to here, this 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 to here. Yeah, it's the same offset, so we can do this now also. I think that's everything. Now let's patch all the connections. Don't need this, don't need this. This. Now we have our nice corner. We'll come back to round it off in a minute. Everything's okay here. Trim this. We'll round this off in a minute. Okay. Seems everything is fine. Now we can do this circle. Go. And okay, we can now round off all the corners. But first we need to find out the radius. This corner is very visible, so we can use this one to take the radius off. Let's say about here. 0.56. How was it here? 0.7. Will 0.7 work here to keep it consistent? Let's see how 0.7 looks. Yeah, kind of. Looks okay. We can use 0.7. Okay. Going on the same path. Here we go. Here we go. There maybe we'll have to see in the 3D phase if it's even possible. I won't be rounding off the internal corners. I'll just leave them as they are here. The only one we have to absolutely do is this one, so the lines connect. Again, I was trying to do the AutoCAD thing, draw a third line and define the circle with 3 tangential lines. You can do this. Let's measure this corner with 3 points. About here. 0.3. Let's cut this off here. The fillet command can have some troubles sometimes with cutting off the lines. It can generate some weird results, so if I help the soft, there's a bigger chance it will work. Oh, exactly. Although that was more of my fault, I clicked in the wrong place. Nonetheless, let's try this again. Okay, here we go. But I think I messed up this circle. Yeah, we'll need it to connect here. So let's draw it again. It was the biggest one, so D7.4. There we go. This corner is fine. Everything is fine. I'll try to remember that from this line up everything is already finished, so I won't be going back there to even check. Okay, maybe let's tackle this piston now. Pistons are very fun to make on the Bionicle parts, as long as you have prepared certain approach to them. I like to do it in this way. First, I pick up the two hinges. This one. This one. And the line between the two centers. Come on. Here we go. Center is our axis of both of those two cylinders, and we also picked up the angle of the sides, so we can use this line to pick up the diameter of both cylinders, the bigger one and the smaller one. There we go. But you might suspect that the distance from this line to the center and this line to the center probably isn't the same, and you can actually even see it that this dimension is much more bigger than this one. And now we will find the what is it called? The median? We're going to divide it but by half, basically. Not approximate. I don't know the word. Wait, actually, let's wait with this. Okay, I did it. Okay, let's do this one more time so you can understand better what I'm doing here. I draw those two lines, and now if I mirror this part from our axis, we'll actually get rid of the original one. Yes, now they're both on the one side. The one from this side disappeared. It's this one here. Now you can see that there's a difference between them. So if we moved this line to this line, then we would have the same gap on this side. So to kind of make both of the sides happy, we'll find a line that's between them. Let's use this one. We don't need this. And now the line is not as accurate to this side But if we mirror it back to the right side, you can see that the gap we have here, we also have here. So the both lines are the same distance from the kind of best lines they could be, and now we can resolve it and do a cylinder out of this profile, and it will be the closest we can pick up to the original size. So now we'll do the same thing with the smaller diameter. Again, let's do it a little quicker. There we go. Now we can get rid of this excess. Just move this here to be sure that we don't leave some random lines and geometry on the line there. Okay, let's extend this. Now the fun part, getting rid of the excess, seeing what we've got. That looks pretty great. I like to leave the center line because we will actually need it in the 3D phase to resolve the half of this profile to make a cylinder out of it. So I'm not going to get rid of that. I'm going to extend it so we can use it later. This is actually unusual. On other Bionicle parts we would be actually done, but this one have this fillet right here. Not sure why, but let's model it how it is, because we are making a recreation. We are not allowed to make decisions about the way this part looks. It might be stupid, but you know, we're doing it the same way someone did it before. Okay, that was a little harsh. It's not stupid, I would just do it different way. Not sure what the reason was here, but it's not stupid. There might be actually a very good reason and I just don't know it. Let's trim the excess. Mirror that. Get rid of the excess. There we go. That looks pretty great. Let's now wait. Actually, let me this. Let me check if everything is working okay with the stream. Okay, everything seems to be working fine. Let's continue. This circle is a little bigger. This, we have a fillet here. What was the radius here? 0.3. Let's see if we can use the same dimension here. 0.3. That looks nice. We can use the same radius here. Let's trim those lines. Okay, so this corner is now modeled fine. This line looks to be tangent to this circle. I hate to be a broken record, but in CAD you would do Control Shift right, choose tangent, pick up the circle, and you could have perfectly tangent line to the circle, but I have no idea why it doesn't work in this NanoCAD. Maybe it's available in the paid version. I'm using free version, but I have no idea why the menu is here, but if you use it, nothing happens. Not even a command shows up here. No idea. So let's do the same trick we did earlier. Let's pick up the angle, make a line that's perpendicular, move this to the circle, there we go. Now this will intersect here. Don't need this. There we go. Trim of the excess. How does it work here? Maybe like that. This is the same thing we had with those cylinders intersecting here. It will actually turn one way or another in the 3D modeling phase, so I'm not really concerned how this corner here looks, because when I extrude this plane and when I resolve this cylinder, they will meet one way or the other, so it doesn't really matter to me. Queen. That actually looks a little better. Let's use it. Okay. Here we are done. Why don't we have this model here? That's weird. Okay, so let's do this attachment point now. So, is this tangent to anything? Maybe to this circle? No? Oh, it might be perpendicular to this. Let's see. Yeah, that looks like it should be like that. And actually this looks to be mirrored from the rotation axis of the cylinder. Let's try if this will work. Kind of. Oh, not really. It's perpendicular to this line that we don't have here. Let's get rid of that for now. How to do this? Okay. Let's do this coin. Wait. The arc here comes with contact in contact to a straight line, but I look at the part 8, they don't seem to be tangential. So this is actually more convenient for us. This little face seems to be vertical, so we can just use a vertical line. There we go. They intersect. We have this little sharp corner here, not tangent. And this kind of angle here, this deviation from this line, is actually a distortion caused by the difference in thickness from here to here, and the part actually doesn't slope off like that. It's all one face. I'm looking at the physical part, and that's how I know. So we won't be doing the slope here. The corner actually looks like that. They intersect here. How the underside here looks? Oh, it's all parallel, but there's a small... Okay, so maybe I'll just draw it and show you without explaining. Maybe this will be faster. This looks like that. What's the offset here? Oh, come on. Arcade, yes. How to check it? Don't remember. I need to... oh, was it the same as this offset? I can't remember now. Maybe? Yeah, I think so. Let's assume this, and we can actually add those two lines supposed to be perpendicular. Not really. It just look like that. If we actually make 90 degree here, 90 degrees, it will not be very accurate. It would cause error. But also, wait a minute. Those two lines, they should be. Oh man, I missed this. I'll have to redo this in a second. But let's finish this first. What was the offset? God damn it. 1.3, maybe 3.5. Yeah, I think it was 3.5. Offset 1.35. We could have checked in our history comment. God damn it! What a waste of time. This is basically what we needed to do. God damn it. That's how you pay for crappy memory. And the egg here was what exactly? 0.7. I thought 0.3, but the 0.3 was from the inside. 0.7. Here to here, here to here. There we go. We'll have to. We'll need the length, the distance from this line to this corner, but I think it will be better to measure with calipers later. Let's just leave it undrawn for now. Okay, get rid of that. That, I guess. Okay, inside was 0.3, so let's do this definitely here. Maybe not, maybe not. No, let's just leave it unfilled. Unfill it. Okay, let's do this now here. This doesn't go as far. This only goes to here, and we have this line here, like that. Extend this. Extend this. And this. There is an extend command, but I find it quicker and easier just to do it by hand. I can show you how the extend works. The theme works like it deletes the rest of the line to the next point where it crosses with something. So the cutoff works like this, and the extend, it's easy to imagine, works exactly the opposite way. It extends to the next feature. So basically we can do this, or we can extend it past the point and trim. It doesn't really matter. Works the same way. Okay, so now let's round off the corners. 0.3. This one definitely yes. This one, let's leave it. Let's leave it like it is. This one yes. Okay, that looks nice. What's the connection here? I think it will turn out in 3D. Let's just do something like that to close off that that loop, this profile. I'm not sure it will look like that. The third dimension will dictate the actual shape. Okay, is this all done? I think so. Let me look at the part. Yeah, that looks okay. We can move on. This thing, okay. This line and this line supposed to be they basically supposed to be one line, but I didn't figure it out earlier. Now you can see that they are almost parallel, not really, because the distance here is a little bigger than the distance here. They are very close though, but nonetheless they are not on the same line. So I will have to move every feature here, and unfortunately this too. So we'll have to all redo this all from scratch. This will be now correct. And the offset was 1.35. This to here. Okay, and the inside the radius was 0.3. Oh, it didn't cut off. Worked fine. Maybe no, should cut off the rest. Yeah, that's what I was talking about earlier. The fillet command sometimes have some problems. I'm not sure what they are caused by and how to well, I can get around them. I don't know how to work with it sometimes. Okay, that wasn't so bad. Nice. So this little section is everything that's left. let's pick up these 3 circles. This one will dictate our diameter and our center of the circle, but this one will only dictate the center, and to have uniform well, actually, let's redo this one too. To have the same diameter, what's the diameter here? 1.89. So let's do 1.9. D 1.9, and same here. D 1.9. Now we can be sure that they are both the exact same size. It doesn't really matter if they're 1.89 or 1.9, or this one would be this or this one this. I just like to make things consistent. The actual possibility is that the guy who first designed this didn't make those holes neither 1.89 or 1.9, but like 2 millimeter. Now I'm picking it up with an error after the ABS shrunk in the mold. It's not extremely accurate. I'm not redoing the same exact thing that the Lego designer did so many years ago, but you know, it's reverse engineering. You have to expect this kind of inaccuracy and just work with it. For features that need much better precision, like connection points, like pinholes, like axles, you would have to work out the perfect dimension the other way. You could measure it with calipers, you could 3D print it and prototype it and check the fit with other parts. You would have to be much more precise here, but when we just pick up the outside curves of some blade or some holes that aren't even connection holes, doesn't really matter if they are 0.89 or 0.9, it doesn't make a difference. And like I said, you have to expect that they won't be accurate either way. So if they are not accurate, no matter what you do, then you can just not think about it and keep moving. It doesn't look like 0.3. Yeah, something's wrong here. But this might be 0.3. Yes, this one is. But this one, I also have the error here. As you can see, there's a gap. Let's measure the radius here. .35. So actually 0.3 should work. How does the 0.3 look again? Let's leave it. Doesn't really matter. The center of the circle. Here we go. Down here. Again, just to close off the loop, the profile. Okay. Let's see. We have this line here. And are they related in any way? No, doesn't look like it. Okay, so extend. We need a circle here. Waypoint. Like that. No, I messed it up. Again, would be nice if this circle would be tangent to all these 3 lines, or at least those 2 lines. How to do this without my favorite AutoCAD command? What's this? Is it point? Point. What does a point do? Oh, you can pick it. No, you can. What? Never mind. How to do this? It doesn't really need to be tangent to this one or this one, but it absolutely has to be tangent with this one. Oh, I know how to do this. It will be another hack job, but I've lost count of the hack jobs we did today, so it doesn't really make a difference anymore. There we go. Good enough. Let's check that we didn't miss anything. Everything looks fine here. Everything looks fine. Alright, so we have... I didn't save for this entire time, god damn it. Thank god that it didn't crash, we would lose all this work. Okay, this side is done, now we can mirror it to the other side. Let's just recheck, everything here looks the same. I will not be modeling the artifacts that I left after the injection molding, especially that they can differ through different parts. Not only you could have different molds and the artifacts would be in different places, even from the same mold the artifacts could once show and the other times not. They could be once above the surface, then they could be below the surface, so it's really a waste of time to model all those artifacts that I left after molding, because you will always get them wrong no matter what you do, so it's best just to skip them entirely. Let's not care about this one, everything looks here okay. I will not be modeling the copyright logo or the part number. I don't need it for anything, so the only difference is this diameter. Okay, don't need this. Trim here, 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 here. This looks fine. Okay, so we are done. Now we can import those flat references to Fusion and do our third dimension and 3D model the part. Okay, so now with the sketch in NanoCAD done, we redo from references both sides of the piece, we can now import those lines to 3D modeling program. I'm using Fusion 360, and we can use the sketch we made to 3D model part with some volume to it. So first we're going to start by inserting the sketch we already do. I didn't use the plane. Okay, here we go. Now everything is okay. There we go. This will be our front, this will be our back. Oh wait, did I do this backwards? That doesn't really matter. Let's start with this part. I like to position the sketch so the reference point, the origin of the well, basically the point where all the axes intersect, I like it to be at the center of the pinhole. Oh man, I hit escape again. Point to point. Okay, and now this half of our part is in the correct place. We can finish our sketch. I'm gonna rename it to more easily find it later. I'm going to name it front. Now we need the other half. So again, the XF, select, okay. Now we need the, wait, let me see. Okay, we need this one. So we can delete this one. We need to mirror line. Okay. And we can move it so they are in the same place, point to point. Okay, now you can see we have both sketches in the same place. This is identifying feature, the circle that's on one side smaller, on the other side bigger. So we can see both sketches because they are transparent. We can save, and I will try not to forget to regularly save our work. I'm not saving because Fusion 360 is cloud-based program that wants you to upload all your work to the server. I don't really need this, and there is also a cap of 10 documents. So to get around that, I instead of saving, I export all my files to my hard drive, and I have access to everything that I need on hand. Okay, so now we can start creating shapes with third dimension from this part. And basically what you need to do is look at the physical part you have and decide what order of operations you are going to do. You need to do which profiles can be extruded at the same time, which profiles are going to cause you problems with some next operations. For example, this this feature here that's going to be extruded from this arc is tapered down. So this entire profile is at the set height, but this little appendage goes down to this plane. So the best way is to do this appendage first, because if I start with this plane and then I'm going to cut off the slope of this part or model it in some other way, I'm going to have to look out for the planes we already made to not cut them, to not modify them. So my general approach to this kind of thing is to do the most complex, most difficult geometry first, and then you can slowly add the easier stuff. So I'm going to start with this appendage, and first let me look at this appendage. What operation I would like to use? If it was straight, this appendage, if it wasn't on an arc, if it was a straight line, it would be very easy, because I could extrude this profile to desired height, and then I could tilt this face down. The problem is that it's at an angle, so if I do this, it won't work the way I want it. It won't work right. The other possibility I have is to use resolve to create basically a cylinder at an angle that would intersect with this plane here and with this profile at a desired height, but I think it would be pretty difficult to do. And the third option is to use a loft. Loft is a very interesting feature. You can see, damn it, I don't know if it will animate or not, I don't think so, but you can create multiple sketches, multiple profiles with multiple shapes, and you can create a shape that goes between them. So we are going to use this one. Maybe it's a little overkill for this little appendage, but this will give us the most control of this part. But so we can create the sketches we need for this loft. It would be very helpful to have some geometry around it first. So we are going to edit the sketch. We are going to section off these appendages that go down, and we are going to extrude this profile, so we have something that we can work from. That was a lot of talking, but I hope that when I start doing what I need to do, I hope this will become clear. Extend. We can section of this. We can section of this. And now we can extrude only this part without extruding this and this. I like to position the plane that I'm extruding from, and this is basically, which plane is it? I can see it. Wait. I like to position the plane in the middle of the part. You could position it on one side and work from one side to the other, but the problem is that there are many features that are in the middle. So if you would do this way, you would always have to go from the one side to the other, and then you would have to move the feature you started, so it's symmetrical on both sides. The better way to do this is to work from inside out. So you know that the features you make are always in the middle and they are always symmetrical. Also, the dimension we need from here to here is much easier to check with calipers than dimension you would need from the center to the half. So that's just a natural way to do this. I'm going to use my calipers now to check what size what width this part is, and it says 738, so it's probably 7.5. We can round it off, and we have some starting geometry. Now we're going to show our sketch back again, and you can see that now I have this face that I can work from. So for example, the profile for this appendage I need on this side can be directly drawn on this wall. So it's just convenient to do it this way. Let me look at the part. Okay. So now let's start a sketch on this wall. And now I can show you the thing I mentioned earlier, why I like to draw in drawing software and then move to 3D modeling software. Because if I want to draw something here, for example a rectangle, I can make a rectangle, and if I don't do anything to it, it's free to move around the way I want. It has positive sides to it and negative sides. Like I mentioned earlier, there are situations where you might actually want this, but if you have a picture and you want to draw on the picture to recreate the shape, then this situation is very annoying to deal with. So to lock this in place, I would have to put a dimension here, I would have a put 2 dimension here, and you can see that the rectangle now can't change shape, but it can still move. So now I have to, for example, put a dimension here. Now it can move only up and down. I have to put a dimension here. And now after 4 dimensions, it's finally locked in place and I can't move it. So it's a really pain in the so it's a really big problem and a pain in the ass to work with. So when I create a sketch I'm going to model from, I like to do it in drawing software, so it's much more convenient. Okay, now we can get back to the job at hand. I have my rectangle. I know that I know it from the physical part. I can see how the shape looks. I can see that the sides of this appendage will be flush with the sides of this extrusion I already made. You can see that I can't move the rectangle up and down, but now I can move it side to side. We can use the dimensions we drew on this sketch already, but again we have to modify it a little bit, because we need a point where this arc intersects with this line and where this arc intersects with this line. The problem is we have fillets right here and a small one right here, so the way it is drawn now, those two lines don't actually intersect and we don't know where this point would be. So to get around that, we're going to extend those lines so they meet our wall, and now we have those points right here, and we can add the rounding fillet later. So we finish sketch, we get back to our sketch. And now, because if I disappear the earlier sketch, you can see that we don't have actually anything that we can use. We have only this one sketch, that is this one rectangle. So to use the geometry from the previous sketch, we're going to make it visible, and we're going to use the command project. So we want this point from this earlier sketch and this point from this earlier sketch to appear in our newer sketch. So now you can see that even if I disappear the previous sketch, the points are still here. And now we can say that this line is going to be on this point and this line is going to be on this point. And with the sketch turning black, it means that everything is constrained. I can't move it, I can't rotate it. It's basically as you want it to be. In general, you want to constrain all your sketches, so you can't accidentally move something on accident. But again, there are instances that it's more beneficial to leave the geometry unconstrained, especially if you are fine-tuning something and you want to see how the geometry will look with this sketch, and then you want to change it a little and see what the difference. So you always want to choose the best way to constrain your sketches for the task at hand. This is one end of this appendage, and now we need another end right here. So we are going to finish the sketch, this rectangle we drew. We are going to leave it for now, and we need to do something similar here on this line. We could create an extrusion from this profile and create a similar wall to this, but it's not really necessary, and like I said before, this might cause problems later. So we can just make a plane here, plane at an angle, at this line. You can rotate it, and we have artificial wall here that we can draw on, but it's not a physical geometry that can cause us problems later. So we're going to start a sketch on it. Again, we are going to make a rectangle. We're going to project the points. We're going to constrain our rectangle to these points. Now you can see that we can move the rectangle up and down. Actually, I'm going to add one more constraint, midpoint. I want this point not only to be on this line, but to be at exact center of it. So now if I try to stretch it down, you can see it stretches the same way up. So I know that the rectangle is perfectly at the center of our part. It's not necessary, you can do this in other ways. For example, you could add a dimension to this rectangle, and then you could say that the distance from this side to the center, I can't because I created, well, let's delete this constraint, and now I can set that the top side to the center equals this, whatever it is. I can change this, and this will update, and it's divided by 2. So if I change it to 8, you can see that this changed to 4. So it's always in the middle. You can enter more complex equations here. I could add 1. I could divide it by some other dimension. So it's really helpful. You don't have to do the math yourself. You can just say that this thing has to be, for example, 7 times bigger than this thing, or this thing has to be as have relation to the other thing as this to this. So it's really helpful, not really needed here. So we can do just the midpoint. Okay, so now I'm going to look at the part, and I see that this side of this appendage needs to be flush with this or this, with this profile. I don't have this profile yet, but I can already measure it, what it will be, and it will be 1.41. So we are going to put 1.4, and we know that this sketch, this plane, when we eventually make it, will be the same width as this this appendage. Now we could use the command loft, but it's not going to have the shape we want. I'm actually going to use it and show you what it will look like. We want to choose our profiles, which we already do. So we add the plus, we want this profile, we want also this profile, no, again, this profile and this profile, and you can see that there is a shape that appeared between those two profiles we made. But if we go to the, let me just set this up, wait a minute, I'm going to set this at home, fit to view. Okay, now we can see that the end of this feature and the beginning of this feature are in the correct place, and the shape of this feature isn't as we want it to be. We want it to go at those arcs, but it goes straight. We could add another profile here in the middle, and it would be a little closer to the arc, because it would go from this one end to the middle and then to the end, but it still wouldn't work the way we want. It wouldn't go at those arcs. So to fix this, we can, in the loft command, add something that's called rails. So the entire command would say start at this thing, at this profile 1, and at this profile 2 right here, but also don't go straight from 1 to the second, but also use the basically the tracks, the shape of the path that we want to go from one place to the other. So we are going to add those rails, and then the shape will have the desired. Wait, again. Oh no, it's okay. Oh, okay, I know how to do this again. Let's save while we're at it. Okay, yes. Now we can proceed. So how to do this? One way to do this is to add those rails that are here in the middle. Actually, I'm curious how it will look, if it will even generate. Here to here. Add those rails, one here, one here. Let's see how it looks. Well, it's actually not bad. What I wanted to do is I wanted to make 4 rails for each of the corners. One here, one here, one here, and one at the 4th corner. But because the shape is pretty uniform and the transition isn't very complicated, I don't think we actually need to do this. I think we can leave this as is. So we actually managed to made a little skip and saved ourselves some trouble, so we can actually move along with the part. This worked out the way we wanted it. And now the basically the same story is with this appendage. This appendage is a little different because it meets this plane that we still don't yet have in different angle. So we will have to take that into account and remember that it actually goes to here. It doesn't just finish here, but basically it's the same story. So instead of commenting, I'm going to go quickly through it because you already know what the problem here at hand is and how I'm going to solve it. Okay, so that's also done. It's important to look at the loft you made from all the sides, that it's just the way you want it and there's nothing weird going on in the other side. Okay, looks good. Now you can see that if you remember how I do it, this entire arc is one arc, so it would be nice if this face would also be basically the same, that we wouldn't have two faces because how we basically made this wait, let me see. Oh, everything's okay. So to fix this thing that happened here, we can use and we can choose this face and we can delete it, and the program will use the faces around it to generate a basically a filling face. So it deletes this one face that was here, this one, and fills the parameter, the hole that is left, kind of using the other faces around and figuring out how this face should look. So this works very nice. We have the shape we wanted. We have one smooth face here. We can continue. I'll export. Let me look at the part. What we have next. We can do the piston next. We could actually already do the easy parts, but since we are doing a little bit more complex things, we can use the piston because it's not really difficult, but it's a fun process, so it will be fun to see. Okay, so we are going to create the piston by using the command revolve. I think I was saying resolve later, I meant revolve. So revolve creates a 3D geometry, 3D body, but not by taking a flat profile and extruding it like we did with this profile, but it's going to rotate it around axis and create a cylinder. So we want to revolve this profile around this axis, and you can see that we have a nice cylinder that also lines up perfectly to both sides because of the splitting, the difference we did back when we were drawing. You can also see that there is a concave shape right here because of the way the piston meets with the other geometry on our sketch. We could leave it like that and then try to patch it, but it might be difficult if it gets covered with other bodies, so the best way is to deal with it now. And we can do it with squaring off this end and also squaring off this end. Now we can edit our feature and we can add that we want to also this revolved. Come on. This. And you can see that the concave convex, I still don't know, the hole that was here disappeared. So we can do this to this side too, and it will be easier to merge with the other geometry later. Okay, so now we can maybe extrude this profile. Like I said, there is no real order to it. You just kind of figure it out as you go, which feature you can do next. Sometimes you make mistakes and you have to go back, like I said, you generate a new geometry that screws with the previous geometry. You have to kind of try to get around a few things, so it definitely happens, but if you put a little thought to the way you approach it, you can save yourself a lot of headache. So again, we are going to extrude it symmetric to both sides, like that, and the distance we want to extrude it to is taken from the part. I'm measuring 1.29, so it's probably 1.3. Oh, I remembered, we forgot to add those splines back. Splines, I mean fillets. It's not necessary to do them now. They would be very easy to add later also, but if we add them now, we won't have to worry about them anymore. I'm going to measure what radius we had here, 0.3. This one is also 0.3, so we can do them both in one operation. We want to fillet this edge, we want to fillet this edge, and we can type our radius 0.3. And if we look from the top, so it lines up with our sketch, you can see that we recreated perfectly the geometry that we kind of disappeared and disabled earlier. Oh, was it? Yeah, here also. Is it 0.3? Yes. So we can edit our fillets, and we want to add this one too. Okay. Where were we? We did this. We'll leave pinhole for later. So now we can add this rivet, this pivot point for the piston. Again, symmetric, and the distance is 3.4. 3.4. Because we added with the resolve some geometry here, you can see that's not supposed to be. When I tell the program to intersect with the geometry, he assumes that I want to cut away this geometry, because he don't know how the program doesn't know how the final shape might look like, so he assumes that because we cross one geometry with the other, that's because we want them to cut to each other. But that's actually not true. We want them to join. We want to add on top of that. 3.4 again. Okay. You can see that it filled up nicely. It looks a little big. Let me check that. 3.4. Well, that's how it's supposed to be. Looks weird, but what you gonna do? I'm going to disappear our sketch, and you can see that from this side everything generated very nicely, but from this side we have some problems. You can see that there are some gaps here and here. We don't want them. In Fusion it's very easy to get rid of. We just point to this face and again delete, and the program kind of figures out by itself how this this shape would look like without this face. Of course, the program doesn't always know exactly what we want to do, and sometimes there might be problems with his figuring out. We would want him to do one thing, he does the other thing. The program doesn't really understand how it looks. So when this happens, you kind of have to either add some other geometry to let the program what you know. So you could point to this face, but also this face, and the result might be different. It might not be, but it might be. You could actually cut away something. There are ways to get around that, but with something as easy as this, everything works great. You don't need to add any more work to it. Same here. You can see that filled up really nice, and also here. Go away. Perfect. Here, go away, and this side looks now really good. You can do the other side the same way. And it looks really well. So we can move on to the next thing. Let me see. Okay, so now I need to extend this profile, but I suspect that it's the same width as this profile. So I'm going to actually check this. This extrusion, not this one, I think. Ready? Yes, it was extruded to 1.3 millimeters. I'm going to measure my part. I'm not going to measure. I don't have really good access to this part because I can't go from in here. So I can measure the width of this region other way. I can't measure for this region how thick it is from one side to the other, but I can check what's the distance between this profile and this wall. So I'm going to measure it on my part. Give me a minute. I want to get this right. And the distance is 2.96. So I can do it this way. I can extrude this profile, and instead of giving it some measurement, I can say just go to this wall. But I don't want to go to this wall. I want to go to this wall minus the measurement I have. So I'm going to offset minus, so go below that, 2.96. I'm going to put 2.95, and I'm going to say do this not to one side but symmetric to both sides. And now I have the wall, and I can check if I was correct about the same width for this place as well for this place. We have 1.6 here and 1.3 here. So it's a pretty big difference. There's a small chance that I measured it so badly that we have this much difference. So probably this region is thicker to allow the flow of plastic inside the mold. So it's actually good that we did it in a different operation. Now we can recreate the other pivot. We can again say go to this wall, but stop 2.45 millimeters before it, and do the same thing for the other side. We can actually check 2.45. The other side 2.45. This is the benefit I was talking about to working from the middle to both sides. If we would go to one side and then try to basically let me show you. If we were going from one side, we would have all the features here flat. We would extrude them to the other side, and afterwards we would have to move the sides to appropriate place, and we would risk that if we would make a mistake, we would risk the possibility that the distance from here to here is actually different from here to here. We don't have to even think about that, because we are working from the middle to both sides the same way, so we know that everything is perfectly symmetrical. Let's clean this up. Perfect. We can actually enable our sketch, check if everything lines up with our sketch properly. Everything looks great. There are no mistakes. Looks really nice. Let's save our progress. With CAD programs, there's always this kind of modeling tree which shows every operation you've done so far. So we can go to the very beginning, and I can go one by one operation, and you can see all the things we did one by one. This is very handy for the thing I did in this modeling process already a few times. If you want to go back to some feature and update it with the knowledge that you have now. For example, I could extrude something else, and see that those things don't line up. So I can go back to the first thing and edit the extrusion length so they line up perfectly. And it's really nice that you can go back. And with this, there's no reason to save your progress as much as possible, because even if you make a mistake and save it, you can always go back and edit, redo, modify the things you already did. So there's really no reason to not to save. You want to save as often as you can, especially if you have a risk of your PC crashing or your program crashing and losing your progress. So you want to save. Okay, so to finish this side of the part and move on to the blade, we are going to tackle this pinhole right now. Let me see how the cylinders were. Okay, I think I know everything. I'm going to open my dimensions that I have written down for easier access. It's a technical drawing I did of some technic part. The dimensions that you can some find online, some dimensions I worked out by myself, by measuring parts, by calculating some things, and I have this little cheat sheet, so when I model I don't have to remember all the dimensions and risk that I mess something up. I can just look at it and see all the dimensions I need right now. So I'm going to move that to the side, and I'm going to use it to make this pinhole. I'm going to extrude this, symmetrical. Looking at my cheat sheet, 785. Next I want to extrude this, again symmetrical, and cheat sheet says 6.15. Okay, the third hole, the third circle is a hole, so we don't extrude anything. So that's done. And now we need to do the cylinders we know are here. So let me just see. Those two faces parallel. No, inspect this to this. Yes, 90 degrees. I want to check with this origin. Is it also 90 degrees? Okay, so we don't have to create new construction planes from the origin. We can use the walls that we have here, and we can sketch on them. If this wall would be at a different angle, we could risk introducing an error, but because they are perfectly at the place we want them to be, we can use them. So let's start a sketch right here. We want, oh wait, I messed up. Although the thing I'm thinking about right now is there are many ways to generate the same shape in CAD programs, but two of the most basic ways to generate a cylinder is to revolve it, as we did with the piston, but you can also extrude it like we did with the pinhole and with all the profiles. If you create a profile that's just a circle and extrude it, it's also a cylinder. So I thought I was going to revolve it, but I had a brain fight again, and the way I set up this sketch, it's set up not for a revolve, but for extrusion. But that works just as well for us, because I showed you the revolve function with the piston already. There's no need to do it again. You can do it quicker way. This to here. We have a sketch, and we can do extrusion. Again, the program thinks we want to cut. We don't want to cut, we want to join. There is option, let me see if it will work. The same thing we did here. So we can say not go to 4 millimeters, we can go to this pinhole, and you can see that the inside of the pinhole stays clean. This is one way to do this, but again, there are many ways to do the same thing in CAD. The other way, maybe quicker, maybe not, is to extrude past this this pinhole we want, and use our function that I showed you already. Delete this face, and also this face. Delete, and it's the same result. So whatever works for you, you can use the instances that one thing may work and the other may not. So yeah, many ways to reach the same destination. This might be also a good opportunity to show you the thing I talked about later, that the with the delete command, the program kind of has to guess what you want to do, and I wonder if I can demonstrate this here. If I choose only this face and click delete, oh, it worked differently than I thought it would, but it also illustrates the point. If I choose only this face and I tell the program I don't want this face here and click delete, the program kind of has to work out how this part would look without this face in place, and he came up with something like that. The whole of the pinhole is cleared out, but the cylinder is left on this step, and this is obviously not what we want. So we can go back and we can modify our input and say, no, I don't want this face, but I don't want also this face, and I don't also want this face. And now click delete, and now the program knows what we are talking about and knows to delete all of that. So it's actually a good way to demonstrate the thing I was talking about earlier. Okay, so one cylinder is done. Let me export, save our progress. Yes. Okay. Now we want another similar cylinder on this side, so let's do the whole thing again. What's the diameter here? 7.4. Wait, shouldn't it be 785? No, 7. Yeah, the length from this to this is 785, and the dimension side from side is 7.4 because this pinhole diameter is also 7.5. So everything checks out. Dimension 7.4. Okay. Let's extrude everything here. Okay. Again, we don't want this. We don't also want this. Everything looks great here. And here is the connection line between those two cylinders that I didn't bother to draw. If I turn on the sketch, you can see that there is no actually. Here is the connection that I didn't bother to draw, because not only it was not necessary to create those shapes, it also might not have lined up if we even if we would draw it. So it turned up by itself either way. Some weird geometry here. Let's delete it. This side is clean. This side. Okay, looks great. So let's just check one last time this part, this region of the part. Everything here looks great. This looks okay. Okay, so from this line down, everything is finished. We can now focus on this part. And this will be really easy. Let's just extrude this first. Symmetric. Let's measure the width on my part. The width is 1.23, 1.22. Let's do 125. Not cut, join. Okay, Now let's export this. No. Did I hit? I don't know what I hit. But I wanted to extrude. Extrude to, again, symmetric. And the distance is 148. So let's do 1.5. I know you don't have anything to cut. I don't want you to cut. It's okay. Calm down. Okay. Now let's extrude those two. The dimension here is really tiny. Let's get this right. 1.1. 1.1. Oh, join. He finally figured it out. Okay. Those are holes, so it's okay. Let's tackle this feature in a minute. Everything here works great. It's okay. And now, when we actually have those two faces that those two features have to meet with, we can come in and clean all the weird unwanted geometry. So this goes into it like that. We also don't want this. You can see that this shape would be very awkward to draw correctly when we were sketching from our reference. So this is another instance of the place where you can just redraw general outlines and let the geometry dictate those connections itself. Okay, this appendage is done. Now let's do this one. Okay, that looks great. And the last thing to do is this feature that is the only reason we have sketch on the other side. Again, million ways to reach the same destination, but I'm going to do it this way. I'm going to do both sides one at a time because the feature is not symmetrical. For this side, we're going to extrude to this plane. Wait, why is it not working? Extrude. Oh, I clicked the start. I wanted distance. To object, join, offset will be minus. It's really hard to fit the caliper here, so I'm going to actually modify this, and I'm going to say go to this face, and the offset will be greater because I can actually rest my caliper on this face. So I'm going to measure it this way, and it's the offset we need is 3.37. Let's do 5. Okay, and this offset, just for curiosity's sake, would have been 0.35 if I had a caliper with blades that could actually fit here. Doesn't matter. This side is done, and for this side I'm going to switch from front to back, and you can see that I have this large circle sketched here, but if I look at the part, I can actually see that it's a little dome that sticks out above this surface. So the way I'm going to do this is I'm going to evolve this feature the same way I evolved the piston, and to draw the side, the cross section from which I'm going to evolve this feature, I need a plane that goes through the center of this circle. As you may know, one point contains infinitely many planes. They can be at any angle as long as they go through this one point. So the actual angle of this plane we need to make doesn't matter in this instant. First, I'm going to create an axis that goes through this point. I'm going to hide the body for a second. No point for me? No? Okay, let's do this the hard way. Edit point. Okay, now it will work fine. So again, axis perpendicular to face at point, hide the body. I want this point, and the plane I want this one. No? Wait. Again, sometimes I have a little problem with Fusion still. So this plane and this point. Why doesn't it work? Wait, am I choosing the right command? Axis perpendicular to face at point. What's the difference between axis perpendicular at point? This might work also by... Why can't I use this one? Maybe I can't use the origin plane. Maybe I have to use a body plane. Let's try it this way. Okay, I have no idea why I can't use the origin plane and I have to use the body plane. What if I had no faces modeled yet? If it would be my first thing to construct. It's idiotic. Okay, whatever. Okay, so now we have our axis that will be rotation point for this feature. Now we need a plane that goes through this axis. You can see that's what I was talking about, the infinite amount of planes that I can make at infinite amount of angles. It doesn't really matter. For this particular instant, it would work the same way. I'm just going to make this plane parallel to the origin for the sake of being neat and clean and consistent. I don't need to see this axis anymore, although it might work for the sketch. So let's just create the sketch. Let's hide the body for a moment, and the cross section of the feature I'm going to make is a part of a circle that's cut off by a line. So this is our profile we want to make, but CAD programs don't like intersecting planes. So if I would choose this whole shape and set rotated through this through this axis, the shape that would go from this plane would go this way. Shape that would go from this loop, from this profile, would go this way, and they would collide. This one would hit this one would hit this one. It just doesn't work that way. So the program wants to the shape to be only on one side of the axis, and then he likes it better and everything works the way it should. Now the axis, we want to use it in the sketch, so I'm going to project it. Now that we have it projected, I can actually hide it. I know that this line should be at an axis. To find the diameter of this feature, I'm going to project the circle from the sketch. As far as the height goes, let me see. Okay. I also need this. So this has to be here. Wait, am I doing this right? No. This point is not supposed to be on the lower plane. It's the point where this our new feature, this dome, intersects with this plane. So I have to raise it up. It will all become clear in a second. Let me just fix this. You will see in a moment why it matters a lot. Okay. And we need the height of the plane. This is also the thing I mentioned, that you can have general idea how you are going to model something, but you just have to figure it out as you go along, and there might be moments when you need to just stop and think how to do the thing you want to do, because the way you want it won't actually work, is basically false, and you are making a mistake. Come on. Okay. Body. There we go. And we are going to find the height of this point again by referencing on this plane. And the distance from this plane to this point. I'm going to take off the model, and I'm measuring 273. So let's put 275. And now I'll show you. Wait a minute. Okay. Now it's clear why. Let me just show it this way. Why it was important to move this point from this plane to this plane. You can see that if I would use this point as the end of the arc would basically meet this point at the same place, but it would have really different curvature, it would have really different radius, and it would not be accurate to our reference. What I caught at last moment was that while the sketch, our reference sketch, is at the middle of the part, we are looking at the part from the top, so the circle, which is actually a line where this plane and our feature, our dome, intersects, is not at this plane, at this height, but at this plane, at this height. So I had to use this point from our sketch that it's this far from our axis, but it's actually on this plane, and the the AEC to be correct would have to go through this point and not this point. That's the realization I had, and the mistake I caught in time and didn't make. So now we have our dome sketched the way we need. We can finish the sketch. We can hide the reference sketch so it doesn't bother us. And now the most satisfying thing to do after setting up a sketch correctly is to do the feature and see how it works out. Oh, come on. There we go. Rotate around this axis. Again, he wants to cut. We don't want him to cut. There we go. Let's click OK. And now you can see that the dome intersects with the right plate at exactly the diameter we wanted. One thing left to do is to clean up the geometry that might have spilled out of the walls. Nothing here, nothing here. Everything looks okay. So this is the only thing we need to fix. This and this gone. This and this gone. Let's see, check the other side. Everything looks great here. Looks great here. Let's just do general. Oh, we forgot about the axles. So we are not quite done yet. Everything looks fine. Now that I look at it, this this arc that creates this face actually looks like it's tangent with this line. I don't remember if we did it that way. They are tangent. It doesn't really matter since they are separated by the wall, so you can't really see or check or really find out that they are not tangent without doing some sketching. But if we didn't sketch them as tangent, then it looks like a mistake. They probably should be. Okay, everything looks great. So we can call it done, except for the axles. Let's do that real quick. Let me open my cheat sheet. Okay. While the pinholes and the outer diameters of the Technic, well, basically beam, are taken directly from Lego pieces and is standard and should fit the official parts well, and the axle is actually sized for my specific 3D printer. So if you would like to use those dimensions, double check that they work well for your application, because the dimensions of the axle aren't the same way Lego does it, but basically the way I found works for me. So keep that in mind. This dimension will be this divided by 2. This dimension is the same as this one. This dimension is the same as this one. times 5. We're going to do the same thing here. We lost a constraint somewhere along the line, so let's redefine it. Okay, good to go. Set some 5. Okay. Now I'm going to add a relief angle to the sides of the axle. Again, it's not how Lego does it, it's the way I do it. Wait, which one did I do? Okay. Let's double check. Yeah, messed up. I did this one twice. So we need to do this one. Looks great. Now the other one. Double check. Looks great. And the one last thing to do is to add fillets to the axles. Those inside corners. Should be 8.5. Those outside corners should be 0.8. Let's check. Everything looks great. So let's save our progress. And now if I show the sketch, you can see that the body perfectly aligns with the sketch, and that's because we worked directly from the sketch. That's the benefit of preparing the sketch beforehand, working with the reference, and while we actually have the sketch, we don't actually, you will take notice that I didn't look at the reference, scan the reference picture once during this modeling process. I looked at the physical part, I measured some dimensions that were impossible to take from the sketch, like the height of every feature, but other than that, the modeling was pretty painless process because of the way it was done. And with that, this part is complete. It's ready now to be imported to Studio to use for digital building mocks. It's ready to be imported to CAM programs like Cura, to slicers, to generate G-code for 3D printers. It's ready to be used as a part of digital kit bashing. It can be cut up, it can be used to make other parts. It's really great thing to have part in this file format, the editable 3D model, because for example, if I 3D print it and I find that the pinhole is too small or the axles are too big or whatever, I can just go in, I can directly edit set face. I can make it smaller, I can make it larger. If I want to print this part without the this axle, I can very easily you could choose faces like that with your mouse in Inventor. I don't know why the program chooses the whole body. Let's try it this way, maybe. Okay, you can very easily delete this face. You can delete even this cylinder, this feature. You can see that the axle was never here; it's completely gone. So this file format is the best way to have parts, because you can do so many things with it. With that, I think I'm going to be ending the stream. I'm really happy that we managed to make this part from start to finish, to do everything in one go. the pirate I chose might not have been the most difficult or exciting one to see being modeled, but I wasn't sure if I chose a little bit more complicated pirate if we would manage to do it all in one go. I also apologize for the time I did the stream. I realized it was extremely early. For me it was pretty early, for for many of you it was the middle of the night, so I realized that it was not the best time to do the stream, but again I was worried that it would take a long much more longer time, and we didn't have all the time we need to finish it. With both parts we are just around 3-hour mark, so it was a nice stream, not too long, not too short. If I do any streams again in the future, I will try to pick a little bit more reasonable time to do this to do this in. And that's basically it. I want to thank everybody who joined to watch my shenanigans, even for a few minutes. I really appreciate your time. I will be posting this live stream to my YouTube channel in one way or another. I'm not sure yet in what form. If I'm going to edit the stream into 15-minute tutorial how to model pirates, or if I'm going to post the entire stream, I'm yet to decide. But if you didn't catch the stream, you can and you are curious how it went and how I modeled the pirates, you can go ahead and visit the YouTube channel. The stream will be posted there in one way or another. Other than that, once again, thank you for watching, for spending this time with me. Please let me know what you thought of the stream, if it turned out okay, if there are some places that I could actually improve, and that's it for now. I will bid you all a good day.